SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on combustion of solid fuels and propellants. So, today we are going to start a new module, and the module is combustion of metals. Here we will talk about the various aspects of metal combustion. Now, the question may come to your mind that why suddenly we are talking about combustion of metals? Why is metal so important? Now, if you recall our discussions during the the ingredients for solid propellants, during that time I think we have spent some time on discussing the various metallic fuels. For example, like we talked about aluminum, we talked about boron, we talked about beryllium, tungsten, titanium, and several other metal fuels. So, those metal fuels are considered to be the fuels for the propellant ingredients or the propellant formulation rather, whereas the HCPV or the polymeric fuel was considered as the binder. So, in actual terminology of fuel, binder, oxidizer, there the fuel is considered to be the metallic fuel only. Although the hydroxyl terminated polybutadiene acts as binder, but it is also an hydrocarbon fuel. Okay. So, there I think we have discussed about the burning mechanism of HCPV with ammonium perchlorate oxidizers in case of composite solid propellant. In case of double base propellant, we have talked about the homogeneous propellant consisting of nitrocellulose, nitroglycerin, but we have also mentioned that aluminum particles may be present in case of composite solid propellant in order to improve the performance. Now, in this module, in general we will talk about different fundamental aspects of combustion of metals, but we will emphasize more on the combustion of aluminum and boron particles, because they are like the prime attractive metal particles for propulsion applications. But if you look at the application point of view, metal particles are also used in different other areas, like of course, solid propellant is one of the areas, solid fuels, like for example, if we think of in terms of like hybrid rocket, their solid fuel and gaseous or liquid oxidizers may be used, and in that solid fuels the energetic metal particles may be impregnated in order to enhance the heat release, and that way it is going to increase the combustion chamber temperature, and which in turn is going to increase the propulsive performance. Now, if we think about some lunar mission base or Mars mission, other planetary missions, their metal particles may be considered to be one of the potential fuels for such applications. There are other metal particle applications like self high temperature metal synthesis, like self propagating high temperature synthesis SHS of metals and production of various metal oxides, even nitride particles, for example, like boron nitrides can be made, which can be used for some structural applications. Metal cutting and welding can also be considered to be like high temperature combustion process, which involve like metal with oxidizers, maybe like oxygen as oxidizers. Metal fires, for example, like there are some fine dust of metal particles which is extremely flammable and dangerous. So, we also need to study those things because there is an explosion hazards if there is a lot of metal dust, particularly like metal cutting industries where there is a high chance of accumulation of metal dust. So, if there is any ignition source due to some stray current, some overheating of the place, or due to some some electrical short circuit issues which may lead to ignition and which may in turn is going to cause some explosion as well. So, combustion of metals have various applications other than like solid propellant application, but in our module we want to restrict our discussions only within the combustion of metals with respect to the application in solid propellants or solid fuels, and then we will focus our discussion towards the combustion of aluminum particles and boron particles, because they are the common ingredients considered for propellant or solid fuel application. Now, first of all, why metal fuels are so attractive? So, what is the prime concern is that we first need to see that we can compare the energetic content in terms of like gravimetric and volumetric heating value. So, you see we have plotted like gravimetric and volumetric heating value of different metal particles or metalloids also, because boron is considered to be metalloid. So, various energetic ingredients, we are comparing their gravimetric and volumetric heating values with respect to the common polymeric fuel or the binder, which is HTBB, or we can just compare with the paraffin wax also. Sometimes paraffin wax is also considered to be the binder for or the fuel for hybrid rocket. But if you just consider the common polymeric binder HTBB, which has been discussed several times during the discussion of composite solid propellant. So, if you compare the heating value of HTBB and the various metal particles, we can see the boron, beryllium, aluminum, then tungsten, titanium also. So, the blue color is the volumetric heating value, and the red color is the gravimetric heating value, means per gram basis, or you can plot it as per kg basis. Here volumetric heating value is very important, because the propulsive systems are volume limited. So, of course, weight is a concern. So, it is like if we can make the compact propellant which can contain within a smaller volume, if you can have more amount of propellant, that is always better. So, basically the volumetric energy density, which is like megajoule per meter cube or megajoule per liter or kilojoule per centimeter cube. So, which substance or ingredients gives higher volumetric heating value, that is actually beneficial for propulsion application. So, if we compare the volumetric heating values for various metallic fuels with the HTBB, we can see that there are many metal fuels which are considered to be like the considered to be the candidates for energetic materials like aluminum, beryllium, boron. Carbon also has like higher energy content, titanium, tungsten, zirconium. Now, if we see that beryllium is actually having the highest gravimetric heating value compared to all the other energetic materials, and second highest in the volumetric heating value. So, beryllium can be considered to be an attractive choice, but the problem with beryllium is that it is having highly toxic beryllium oxide. That is the major reason that beryllium is not considered as the energetic particles or energetic ingredients for solid propellant application. So, the next available candidate is the boron, which is considered to be one of the attractive energetic particles for solid propellants or solid fuel application. However, due to its high melting temperature, so the melting temperature of boron is in the range of like 2350 Kelvin, something around 2348 Kelvin, and the boiling temperature is also kind of extremely high, it is like 4273 Kelvin. So, due to its high melting and high boiling point temperature, it has been observed that the complete combustion has not been possible for micron size particles, and that is the reason that the micron size boron particles has not been successfully incorporated in any of these existing solid propellant any of the solid propellant formulation or solid fuel formulation, because micron size boron means it is going to cause some ignition delay, it is going to cause ignition delay there. I would rather say like longer ignition delay. So, longer ignition delay means it is going to be difficult to burn the boron particles within the given chamber residence time, because you see the propulsive devices, these are kind of high speed vehicles. So, the amount of time present within the combustion chamber. So, if there is a flame like this, so the particles will be impregnated in the propellant grain. So, they will come and burn in here within the flame, and the oxide products will come out, energy release will take place and will go out through the nozzle, it will expand through the nozzle, but the given residence time may not be sufficient to burn the micron size boron particles fully. So, although the heating value is very attractive, but the micron size particles combustion within the given residence time is very difficult. That is why the micron size particles are only micron size particles are not very attractive energetic ingredients for solid propellant applications. However, recent advancement of the nanotechnology, the nano size boron particles have smaller or shorter ignition delay time, which actually helps into burning the boron particles within the given residence time. So, residence time does not impose much restriction on the ignition delay of the nano size boron particles. So, this makes the nano size boron an attractive choice. So, the nano size boron becomes an attractive choice for propulsion application, because we can see that the volumetric heating value of boron particle is almost like 136 kilojoule per centimeter cube or 136 megajoule per meter cube. So, we can say it is almost like, if you compare this one, this is close to about 42 or 43. So, it is almost like 4 times of the common polymeric binder, which is HTBB, and that is why it makes it highly attractive, and that too the nano size boron particles. Now, if you look at titanium, titanium also poses high volumetric energy content, but it has not been utilized because of its high cost. Of course, the nano size titanium particles are not easily available. So, that is the reason, although it is having theoretically it is having the high energy content, but because of the high cost and the unavailability of nano size particles, titanium has been used in a practical propulsion system. Now, major focus have been given so far on the aluminum nanoparticles, because nano size aluminum particles are commercially available, and if you look at the heating value of aluminum nanoparticles, the aluminum, you can see the volumetric heating value is quite higher for aluminum nanoparticles compared to HTBB. So, that is also a choice, and there have been numerous studies available in literature on the various size of aluminum nanoparticles on the propulsive performance of solid propellant or solid fuels. So, our discussions finally will focus more on the combustion of the aluminum particles and combustion of boron particles. As I mentioned in the beginning of the lecture, that we will put more focus on these two particles. Now, another particles, if you look at tungsten, tungsten is also having high volumetric heating value, but the problem with tungsten is it is also having like very high melting temperature, which is about 3695 Kelvin, and the boiling temperature is also kind of very high, extremely high. It is like 5828 Kelvin. So, that makes it difficult to use the tungsten particles in the propellant formulation. However, there is a hope that there is a hope that the size reductions of the tungsten particles may be useful for propellant application. Just because we should remember one thing, although melting temperature and boiling temperatures are extremely higher, but igniting titanium does not require much energy compared to like boron particles, and the temperature range for ignition of tungsten particles are in the order of like only 700 to 800 Kelvin, and in fact, the reaction can be faster if the temperature of the ambient goes beyond like 800 Kelvin. So, there is a hope that tungsten powder can also be useful if we somehow can manage the high cost and the size range if we can maintain. So, that way the tungsten can be another potential choice. Of course, its gravimetric heating value is comparatively very low compared to HTPB. Now, another important consideration is the density of the solid fuels. If you look at the density of the different solid fuel, different metal particles compared to HTPB, except lithium, I think if you look at except lithium, we can see almost all are having like very high energy, very high mass density. You see, there may be a mistake in this data probably. I need to refer to literature. This is some typo mistake. So, if you look at the density of aluminum, beryllium, boron, carbon, for all the metal particles, we can see except lithium is having like high density. So, why high density is important? Because in case of the performance of propulsive system, higher volumetric is one important. The other important parameter is the density, because it is not only ISP, but it is rho ISP is important for volume limited propulsive or volume limited propulsion systems. So, higher the density will, there is a chance that is going to give. So, it is a combination of like density and the volumetric heating value. If you have high volumetric heating value and high density, that is definitely going to give us like rho ISP higher, and that is going to be beneficial for volume limited propulsion systems. So, now after this basics understanding of why energetic particles are important for solid propellant application, we will now focus on to understand the metal combustion classification, because the metal particles are not exactly the similar like the hydrocarbon fuels. There are different metal particles are available, and the burning characteristics of metal particles are also not be the same, because some metal particles are having very high melting temperature or boiling temperature. Their oxide counterpart is also having like higher melting temperature or oxide temperature. So, if we look at the various metal particles corresponding their oxide volatilization dissociation temperature, we can try to understand that whether the metal particles burn in vapor phase, means everything will be in gaseous state and they will burn, or the metal will burn in a heterogeneous combustion mode, or like in a surface reaction is going to take place, not in vapor phase. So, we have to understand this metal combustion classification, and it has been nicely given by one criterion is called Glassman criterion. Now, before going into that, I think we should first try to understand one important consideration is that if you try to burn the metal particles, the flame temperature of metal, it has been reported by von Gross and Conway during like early, I think late 1950s. It has been reported that the flame temperature, they have introduced a concept that the flame temperature of a metal was limited to the boiling point of the oxide, or we can say like the dissociative gasification into species other than metal oxide. So, what does that mean? That flame temperature is not going to go beyond the dissociative dissociation volatilization temperature of the oxide, and that is going to give the limit of the flame temperature. Now, most of the metals have high boiling point temperature. So, the metal to burn in the vapor phase, the oxide vaporization or dissociation temperature must be greater than the boiling point temperature of the metal. Now, if that vaporization dissociation temperature is less than the boiling point temperature of the metal, then of course, they will burn in a heterogeneous combustion mode. So, this concept is given by Glassman, and it is known as the Glassman criteria for vapor phase combustion of metal. So, we will try to understand this by comparing the boiling point temperature of metal, and we can consider the vaporization dissociation temperature of the oxides, and by comparing that we can come to an understanding that how this heterogeneous combustion and vapor phase combustion take place. So, the condition says that the Glassman criteria, if you look at the Glassman criterion, it says that why it is happen in the limiting flame temperature results from the fact that the heat of vaporization. So, this concept is actually given in early 1958 by two scientists called von Gross and Conway. Their research reported this concept that flame temperature of metal oxide was limited by the boiling point of the oxides or the dissociation gasification into species other than metal oxide. So, the limiting flame temperature results from the fact that the vaporization dissociation of the metal oxide formed is greater than the available energy to raise the temperature of the condensed phase oxide above its boiling point, and that is actually the limiting condition which imposes the whether it is going to be a vapor phase or the heterogeneous combustion. So, what essentially the condition is that vaporization dissociation the heat of vaporization and dissociation of the metal oxide is greater than the available heat in the reaction. So, that is basically the available, where QR is known as the heat of reaction of the metal at the reference temperature. So, reference temperature here is given as 298 Kelvin. The H0T volatile is given as the, or you can write the difference actually, that H0T volatilization minus H0T H0298. So, this is basically H0T volatilization minus H0298 is the enthalpy required to raise the temperature to its volatilization temperature. Basically, to raise the temperature of the product, temperature of the product to its volatilization temperature at reference pressure, that at the pressure of concern, at concern pressure. Okay. And we have in many occasions we have seen that for a condense phase fuel droplet to burn in the vapor phase, the gas phase temperature must exceed. So, in order to have like vapor phase combustion, the gas phase temperature must exceed the boiling point temperature of the metal. Okay. So, if we take some example, we can understand that if the metal has to burn in vapor phase, in let us say in oxygenized oxidizer, this will be decided by the metal's boiling point temperature compared with the temperature at which metal product oxide is decomposed or dissociated to gas phase molecules. So, that is actually this this heat of, we have not defined this one, that what is the heat of this one is defined as the heat of vaporization dissociation of the metal oxide, Okay. So, what essentially we are understanding here is that, so if the metal has to burn in vapor phase, the gas phase temperature must need to exceed the boiling point temperature of the fuel droplet. So, if we need to burn the fuel droplet, let us say metal droplet we want to burn in vapor phase. So, the gas phase temperature must have to be higher than the boiling point temperature of the fuel droplet. Now, most metals are having like high boiling point temperature. So, it is very likely that metal to burn in the vapor phase, the oxide vaporization, dissociation or volatilization temperature must be greater than the boiling point temperature of the metal. So, we need to have like the volatilization temperature of the oxides must need to be greater than the boiling point temperature of the metal, boiling point temperature of metal. So, if this condition is met, then metals can burn in the vapor phase. Now, if the oxides vaporization dissociation temperature is less than the boiling point of the fuel, combustion will proceed in the heterogeneous mode, and the flame will the burning will take place on the particle surface, and this concept of heterogeneous combustion or gas phase combustion is given by this Glassman criteria. Okay. It has been given by this Glassman criterion. Now, if we compare the table here, see this table is listed the boiling point temperature of various metals and their corresponding oxides, the volatilization temperature of those oxide are given here, the value of delta HF, value of delta H volatilization is given, this value is also given. So, if we simply compare the boiling point temperature of the metal compared to its volatilization temperature of the oxide, we can get an idea about whether it is going to happen in a gas phase or the vapor phase combustion, or it is going to happen in heterogeneous combustion. So, according to the Glassman criteria, what you can say, you see beryllium, which is having like the boiling point temperature of 2741 Kelvin, and the beryllium oxide is having the volatilization temperature of 4200. Similarly, in this category we have chromium, which is 2952 and its oxide volatilization temperature is 3280, iron 3133 3400, hafnium 4876 5050, magnesium 1366, magnesium oxide 3430. So, what about titanium? Titanium is also 3631, titanium oxide is 4000, aluminum 2791, boiling point temperature of the metal, aluminum oxide is 4000. So, they are having the capability to burn as vapor phase diffusion flame at 1 atmosphere, because this reference is given as 1 atmosphere pressure and oxidizer as pure oxygen. So, they can have the vapor phase diffusion flame at 1 atmosphere pressure and in the presence of oxygen as the oxidizer. In contrast to that, if you compare the boiling point temperature of metal and corresponding volatilization temperature of oxide, we can see boron is having like 4139 versus 2340. So, actually the oxide volatilization temperature is less than the metal boiling point. If you look at the silicon is having this 3173 versus 2860, zirconium 4703 versus 4280. So, it is less than the boiling point temperature of metal. So, we are expect that there is a chance of having like heterogeneous combustion for these type of metals. However, in case of boron, that there is a sufficient energy to vaporize the oxide, but still the energy available to raise the temperature of metal is to boiling point, it is insufficient to burn in vapor phase. So, these are the different example of vapor phase combustion versus the heterogeneous combustion, and we can actually consult this table and we can get an idea about how they are taking place, consulting the Glassman criterion as we discussed over here. Okay. So, I think we can continue this thing again in the following lecture. Okay. Thank you.